Right, welcome back. So let's look at your theory book worksheet 5 for the questions on moments and principle of moments. So let's take a look at the first question itself. The first question is a tree trunk. It is not evenly distributed, the mass, and its thickness is also not evenly distributed. So what happens is this tree trunk itself has a weight of 1,000 newtons. This weight acts through the center of gravity. So as you can see, R is the center of gravity here. And that is where the mass will act down, which is 1000 newtons here. Okay, it rests on two supports Q and S. The center of mass is at R, the minimum downward force that must be applied at point P. So they want to apply a force at point P here, that is downwards, such that they can rotate about Q. So Q is your pivot, and such that it will not touch S at all after that. So you can see there's one force on R, which is 3 meters away, and there's one force F here that is 4 meters away. This gives an anti-clockwise moment. This gives a clockwise moment. So that itself tells us that this is the principle of moments. So they want you to find F. So taking moments about Q. So instead of just writing this, you want to write down the formula that you use. Using principle of moments and taking moments about Q, we can calculate the clockwise moment and anti-clockwise. So this itself, the presentation is not good, but never mind. Let's move on for this first. We can talk about the presentations for the subsequent question. So it denotes here as Fp, the force at P itself. The distance is 4 meters from the pivot. Next is 100 newtons, which is the weight, and the distance is 3 meters here. So from here, this equation, you can find what is Fp, which is 750, and answer is B. Let's look at section B, question 2. For section B, question 2 itself, figure 5.6 shows a balanced uniform beam that is supported at its center. So this is the center here. So center of gravity is here. Find the ratio of mass A to mass B. So they want you to find the ratio of mass A and mass B. So we know that W is equals to mg, where W is weight, M is mass, G is the gravitational field strength. So using principle of moments and taking moments about the pivot, anti-clockwise moment of A, because A has a weight that goes downwards, it gives a anti-clockwise. B has a weight that goes downwards and it gives a clockwise. So that's why there's two different moments. If we balance them out, let's take a look. So A has a weight of equals to MA times G. W has MB times G. So that's why they have MAG here, which is the weight for the anti-clockwise moment. MAG will be the weight. 30 will be 13 cm. He said, Mr. Song, why don't we change it to meters? It's fine because after that you'll cancel out each other also. Next, WB, which is MBG, times 40, which is the distance away from the pivot. So by doing the math, you'll find that the ratio of MA is to MB is 4:3. Okay, so let's look at part B. Figure 5.7 shows a 1 meter long beam. So they will tell you that this is 1 meter. That means from here all the way to here is 1 meter. It's pivoted about P, so this is the pivot. A mass of 2 kg rests on the beam, so there is mass, that means there's a force, weight. We can automatically calculate that the weight W is equals to mg, which is equals to 2 times 10, which is 20 newtons, so that will save us a bit of trouble. And it's 60 cm from P. At Q, the beam rests on a support that exerts a force R, so there's another force R here. Because there's a support, it pushes it upwards. Calculate the magnitude of R. So using principle of moments and taking moments about P, anti-clockwise moment equals clockwise moment. So let's take a look which is clock and which is anti-clockwise. R goes upwards, so it's anti-clockwise. The weight of this 2 kg block, it goes downwards, so that's why it's clockwise. So anti-clockwise will be R times 1 meter, which is 100 cm. The weight is 20 newtons, so I've already calculated in advance. The distance is 60. And then we can find out what is R, which is 12 newtons. Okay, so basically it's just using the clockwise moments and anti-clockwise moments to balance each other out. Okay, let's look at the next question. Question 5. Figure 5.10 shows a child balancing toy. It consists of a light rod that's suspended. Light means it is likely to be massless, no mass. Assume, so that we don't have to consider too many factors. Two weights 1 Newton and 2 Newtons are suspended from a light rod. The weights are free to slide horizontally. Okay, determine the moment about t. They want to find the result. That means clockwise and anti-clockwise, what is the result? So what they did here was they first, let's say this is clockwise, this is anti-clockwise. Okay, so what they did first was they find the moments for each of them. So the clockwise moments will be equals to 1 times, in this case, because it's at the center, from here to here is not 20, take note it's 10 cm. So in this case, I'll put it at 0.1 meters. This will tell us that this is 0.1 Newton meter. I'll calculate for this side, clockwise moments. Let's not forget the moments. So this is equals to 2 Newton times, similarly here is also 10 cm, 0.1 meters. That will give us as 0.2 Newton meters. So which one has a bigger moment? The anti-clockwise or the clockwise? Yep, the anti-clockwise. So in this case, you take the bigger one minus the small one. So what you will get will be 0.1 Newton meter. And because it is bigger, so it is the anti-clockwise that is bigger. So this is your resultant moment. What is the result if both sides are trying to balance out? Next, given that the maximum possible distance between the two weights is 20 cm, okay, state which weight should be moved. Why do they want to move? So that it is balanced again. So that you can release your hands, the two toys will be balanced. So determine the distance the weight should be moved. Okay, so let's take a look. Since your clockwise, anti-clockwise moment is very big, so what you want to do is to make it a bit smaller. So you want to shift your 2 newtons in this direction. You want to lower your moments because now your moments is 0.2, which is much bigger than 0.1. So you want to lower these moments. Make sure that these moments go down. So how can you do? Either you decrease the mass, but you can't change that, or you change your distance, which is this. So make your number here smaller. So how shift it in? So let's do the math. Let the distance of 2n weight from point T be d. So they assume, erase all of this. Oh, sorry. Okay, so what they do is they assume that your star you're going to hang somewhere here, and this distance they take it as d. Okay, so in order to be balanced, this is a setup that they have. So they tell you, okay, your star is 2 newtons, 2. Let's multiply by the distance d. So this will be your anti-clockwise moment. Let's find for your clockwise moment, you take 1 times 10 cm, which is 0.1 meter. From here, this equation, you can find that d equals to 0.05 meters. So your object must be 0.05 meters away from the pivot. Okay, so how much must it move? Because they say how much should it be moved? You take 10 cm minus 0.05. So you end up how much you must move 5 cm towards point T. Okay, so this is for part 5. So let's continue. So one thing that's not good here is because they did not state the sum of the clockwise equals the sum of anti-clockwise. So what should we do? We should be writing this statement, or maybe not this, because anti-clockwise moment is equals to clockwise moment. We should write this inside there, inside here. Okay, so that we at least will not make a mistake when we are doing our correction. Set the magnitude of the force in the strings. Okay, so let me redraw the whole thing so that's easier to understand. What we have is a balancing thing. We have one star here, which is 2 Newton. We have another object here that is 1 Newton. It is balanced by a string, which is T. So they ask you, if this is 2 Newtons downwards, 1 Newtons downward, what should T be? They are balanced, right? So the vertical forces are balanced. So T will be equals to 3 Newtons, 2 plus 1. because it must be balanced up and down. Okay, so that's the tension in the string T. Question 1. Define the moment of a force as state is SI unit. The moment of a force is the product of the force and the perpendicular distance from the line of action of the force to the pivot. SI unit is Newton meter. So you must know the definition for moments. Set the principle of moments. The principle of moments is that when the body is in equilibrium, the sum of the clockwise moments and about any pivot is equal to the sum of the anti-clockwise moments about the same pivot. So the thing here, you must be able to state that the body must be in equilibrium first. Sum of the clockwise moments about any pivot is equal to the sum of the anti-clockwise moment about the same pivot. So these are the few things that you must have. The points must be there. Okay. Okay. Figure 5.11 shows the same force F being applied to the metal rod positions A, B, and C on separate occasions to lift a large stone. State the position A, B, or C in which force F exerts the largest moment about the small stone. So you want a largest moment. So if you want a largest moment, there are two situations. Either your force have to increase or your perpendicular distance have to increase. So in this case, they say his force is fixed. So the only other way to increase the moment, because your force is fixed, the only other way to increase moment is to change your distance and make it larger. So where will the position be? Okay, position B will be better. Why at position B, the perpendicular distance of the line of action of the force to the pivot is the longer. So we want the perpendicular distance, not distance, must be perpendicular distance of what? Of the line of action of the force. What is line of action? If your force F is like that, line of action is this line, a dotted line that traces of the force to the pivot. So from the pivot here, so this is the pivot. The distance from here all the way to here, this is your distance D. Okay, this will result in the largest moment about the pivot. Then you say, but position C is also about the same. Now we got to be very careful because position C, line of action, let me erase the previous one first. Okay, this is a pivot. Position F, your line of action is like that, which means that the perpendicular distance from the pivot here is this direction, which is much smaller as compared to at position B. Okay, so that's why C is not correct. Next, part D. Figure 5.12 shows an angler holding a stiff fishing rod in a horizontal position to support a fish of mass 3 kg. So your fish has a weight, and your weight is 3 times 10, which is 30 newtons. His hand here acts as a force. His supporting hand here is the pivot. Okay, calculate the force needed to keep the rod in the horizon. That means they say if it is in equilibrium, how much force is F? So let's use and do the question. Use principle of moments and taking moments about the supporting hand. This is not good because you got to include that the sum of the anti-clockwise moments is equals to the sum of clockwise moments. Okay, you must write this inside here before you do first. So why? Because your F causes the rod to turn this way, which is anti-clockwise. Your fish causes it to turn this way, which is clockwise. Okay, for those who are not able to see, 30 is here. So let's use anti-clockwise first. So anti-clockwise will be here. What is the force? F. So we put F. What is the distance? 30 cm. So we put at 0.3 meters. How about for the other one? We take 30, 3 times 10. And the distance will not be only 90. The distance will be 90 plus 30 because you want it from the pivot. The pivot is the hand here. So it's 90 cm plus 30 cm. That will give us as 110 Newton. Sorry, 110 cm or 1.1 meter, which is what you have here. Okay, so you do this too, you can calculate for F, which is 120 newtons. So the hand must exert 120 newtons. Okay, so otherwise we will end off here. Thank you.